Let's crack part 3 of this video. We have decided that because we're on the point of tipping with SM, that we've got no weight on this pivot at C, and so we've got a reaction of 0 newtons, because the reaction is always equal and opposite to whatever force you've got there. And that means the whole system is balanced on this point here, so all of the weight is going to be carried by that pivot there at D. Okay, so some of you may already have seen over here that all of these, we can do something very simple and we can resolve, even though we don't know R or W, we can resolve the forces vertically here. So I'm going to do that first. Sometimes that gives you a really useful little piece of information. So if I resolve vertically, what have I got? Well, the two downward forces are 120 newtons and W, which is what we're trying to find, 120 W, and they're going to balance with the upward force, which is the reaction. So that's what that pivot is having to take the whole of the weight. Now we might come back to that. You can see it's a simple equation with R and W. Always bear in mind we might end up with another equation with R and W in it somewhere else. We might be able to avoid that though, because again, we can choose moments to be around a certain point. So around which point though? So again, there are a choice. We can take moments about any point in this system. If we took moments about A, we'd have, well, we've got nothing going on here, so we can ignore that one. The force is nil, so nothing going on there. We'd have a force of 120 twisting it to sort of pivot downwards. And we've also got W pivoting downwards. Now we know all these distances, so we could add those two together and balance them out with R. And you can see we'd get another equation with R and W in, and combined with the one that we've got already, we could work out R and W. So it would work at point A. Point C is the next one along. I could take moments about there. I'd have a similar kind of arrangement to if I did it about point A. Weirdly, I could take moments about 120, about this centre of mass here, a centre of gravity, and we would have a force going upwards and a force going downwards. So again, I'd get an equation in R and W. And you can see where I'm going next. If I consider this point, D, I will get an expression that doesn't include R. The only two forces that are trying to twist around this point are 120, which is trying to make it go that way, and that's balanced out by this W here that's trying to make it go the other way. So that has a great advantage of we won't have an R in our equation. We could also take moments about B. There's one little, and that is what force is being eliminated if we take moments about B? Well, W will be eliminated. So if we're trying to find the weight of the rock, we want to find W. So that's that one's not going to work. So I'm going to D as my clever choice, my point D, and that means I don't need to resolve, don't need to use the equation I just found. So D, we have distance between D and the 120 newtons. Well, that's just the rest of that 0.75. I make that to be 0.25. So that's 120 times 0.25. And that's going to balance out with W. And how long is this bit of rock? Well, I've got a metre there, 0.75 metres here, and the whole thing is 3 metres. So we're going to go with 1.25. add those together, you should get 3 meters. Yeah. So we can work out all those distances. So I've got W, the force, times perpendicular distance, check, 1.25. And that will give me a way to find W. So on this side, this is just a quarter, so that's 30. Let me know if I get any of these wrong. So W is 30 divided by 1.25, which is something or other. You might have to work that out. I haven't got a calculator on me at the moment. So 30 divided by 1.25. Let's see how quickly I can do this. That's 4 of them. And then there's 6 of those in there. So I make that 24 newtons. Quite a heavy rock. Okay, lovely. The third part is the magnitude of the reaction at the support of the point, the magnitude of the reaction at D. So that's that R that we labelled up. Billing's coming in really handy. Nicely, we don't have to take moments again because we found this earlier. And I'll post a photograph of all this page of work as well. So R is just W plus 120. So for C, we can use the fact that we resolved earlier, and that is 24 plus 120. So R is 144 newtons. So it's got the whole weight balanced on it. That's the 24, the rock, plus the weight of the plank. And the final part is just asking how you have used the model of the rock as a particle. So what is it that we have ignored, if you like? So the rock is a particle in this model. Because what? Essentially, I think about what we might have ignored here. We've balanced it. I would say the main thing is we balanced it right on the very end of the ruler. And you could see when I was balancing the ruler, if I do that again, because we're done with the question. If I do that again with the ruler and I apply a force, it's very hard to get it right on the end of the ruler here and get that tipping point. I actually had my finger a bit further in. So we've modelled it as a tiny speck that's sitting right on the very end here. We could try and get its centre of mass over the end, but in reality likely fall off the end. So that's a bit unfeasible to get it right on the end of the plank. So the particle element there is just that we has no volume and its centre of mass or centre of gravity, where its mass or its weight is said to act, is precisely at the end. B. For 1 mark, you don't have to go into a huge amount of detail, but it'd be great to see phrases like no volume or centre of mass, or, you know, you can say this would be impossible. We could model it so that it's further in from the end, and that would be more possible. Okay, that's it. Lovely speaking to you. Wish you could yell back and give me some feedback. Maybe post something up. Thank you. Bye.